Welcome everybody to the last Atto Fridays talk of the season. Our speaker today is Professor Sivarama Krishnan. He is currently Associate Professor at the Indian Institute of Technology, Madras, Chennai, India. He is associated with the Quantum Center for Diamond and Emerging Materials for the Department of Physics there. And he also holds a visiting position at the Max Planck Institute for Kernphysik, Heidelberg. And earlier, he held a postdoctoral position at the Tata Institute of Fundamental Research and Research Scientist at IBM Semiconductor R&D Center. He graduated with a PhD from the Max Planck Institute Heidelberg. And he's passionate about teaching physics and optics to young students, particularly to build indigenous experimental setups and communicating aspects of science to broad audience. Very good, because today we have people on YouTube, we have people following on Zoom, and we have people from pretty much everywhere. He will talk about photoexcited superfluid helium nanodroplets, a versatile playground for Atto and femto-second dynamics. So we're going to hear about liquids. We heard a lot about solids. It's great to have you all here. And we are ready to start. The floor is yours, and welcome.
Thank you, Carla. Just to confirm once again, I hope my audio and video are fine. I've just shared my screen as well. Okay, so thank you very much, Atto Fridays and Quantum Battles team for having me here for the closing Atto Fridays talk of this year. And it's indeed also my honor to present this to an audience as diverse as what we have here and as international as it gets. In this presentation, I hope to walk you through a considerable part of our work and possibly even try and convince you that this very interesting system, helium nanodroplets, are indeed a versatile playground for attosecond and femtosecond physics. So this work itself has been done entirely in collaboration, in a close partnership with Professor Marcel Mudrich from the Department of Physics and the Astrid Synchrotron facility at Aarhus University. So we ourselves do not own a helium nanodroplet machine yet in India. We performed all these experiments at various European synchrotron facilities. And right at the outset, I should also acknowledge the team of young researchers, mostly PhD students and postdocs who worked with us both from my group here at Chennai and in Aarhus, Keshav, Shubhendu, Sudha, with an affiliation in another institute in Pune, and from Aarhus, Al-Taif, Jakob, and beyond, who's now moved to another group. But then a work and project of this type is often only possible if is the top of my screen obscuring the view, Carla?
It's all fine. It's all fine.
Okay. Okay, yeah. Okay, cool. So yeah, so all of this has been possible due to the wonderful collaboration I've had the opportunity of building and keeping together with my colleagues both in India and overseas. As I said, all this has been possible through the strong partnership with Marcel and his team all the way from my PhD days, and we have been working on various problems of interest in with helium nanodroplets. A majority of our experiments that I'll be talking about today were done at the Elytra synchrotron facility at the gas phase beam line, where Robert Richter and Marcello Coreno are usually our points of contact, and we are very happy to collaborate with Carlo, Kevin, Monica, Patrick, Daniel, Nicola, and Stefano at the gas phase and cheapo beam lines over there. And much of this work indeed started with Marcel's affiliation in Freiburg with Frank Stinkermeyer, who leads the helium nanodroplet group there in Freiburg, and actually is the face of droplet physics in Germany, along with colleagues from the Rostock group. It's always a pleasure to work with Aaron Laforge, who again has an affiliation all the way from MPIK to now with Connecticut, and it's fun doing beam times with these folks. I've been associated through a Max Planck partner group with Professor Thomas Pfeiffer and Professor Robert Mosama at the Max Planck Institute for Current Physics, which is also my alma mater, and it's indeed wonderful to collaborate with them. And two new avenues have opened up through the CEFIPRA grant and the DST-DAD grant with Nicola Sisura and Milutin Kovachev and Uwe Mogner, respectively. At the Indian end, our own students at IITM, whom I mentioned, and also an important partner in research from the Indian end is Professor Vandana Sharma from the university called Indian Institute of Technology, Hyderabad, a sister institute to ours. And we have a joint PhD student, Sanket Sen, who will also be graduating soon. At IISA Pune, I collaborate with Bas Bapat and the students, Sudhasatwa Mandal and Arnab Sen, and from the Tata Institute with Professor M. Krishnamurthy, who's now the director, and Dr. Ram Gopal. A lot of this mobility-driven research is supported generously by the Indian Institute of Technology Madras funds, but predominantly by the ICTP, the Indo-Electra POC funds, as well as the India DAISY program for the work done at DAISY. DST, the Department of Science and Technology, is a great enabler in the process too. So in our own on our own site, I essentially am located at the southeast coast of India at I think what is India's oldest modern city, Chennai. Earlier it was called Madras. And in Madras, we have one of the 6 first-generation technological universities which are modeled along the lines of the tech TUs in Germany and Europe, as well as the tech institutes in the US, from whose genesis starts from almost the time when India became a free country in the mid-50s onwards. Our institute has about 9,000 plus students. Now it's probably even more. And we are ranked number one by the so-called local rankings, the Indian national rankings among engineering institutes, which is an honor to have, but I'm pretty sure we share this with some of the eminent institutions like the other IITs across India. But then if you visit us, which you're very welcome to, and this is an open yet serious invitation to come to us, you will see a few very remarkable things. We have excellent flora and fauna. We have a translational research institution called the Research Park, which is quite an establishment in itself. But then you also see a road named after a German city, Bonn Avenue. This is because IIT Madras was started in collaboration and with generous funding of the former West German Republic, which of course is now just one Germany. So this is really a multicultural pot boiling in this part of India. Before I proceed, I must also say that the city of Chennai was hit by a cyclone recently. So that's not to bring up domestic issues, but indeed, if there is one thing I want to sort of remember and thank at this point, it's the spirited people of the city who basically brought it back to its feet within 48 hours. Otherwise, I could not even have joined this seminar because of the imminent outages that such events bring. So that aside, the outline of my presentation today is as follows. I will motivate this talk very briefly and take us through this wonderful system, helium nanodroplets, which I have myself been involved with studying for about 15 years now, and I probably don't see any reason to stop that. And I hope to convince you that there is a lot of room and time at this bottom, which is the nanoscale or sub-nanoscale with helium nanodroplets. We will look at the photoexcitation in these droplets. We will walk through the basic single active electron physics and understand the electronic structure. Then we will take up a couple of instances of correlated electron dynamics which ensue in these systems upon EUV photoexcitation, prominently interatomic Coulombic decays, which are very well measured using coincidence spectroscopy. Indeed, I will be only skimming the surface of ICD phenomena and helium droplets. Even one whole talk is probably insufficient to convey the details or even the landscape of ICDs in just doped helium nanodroplets themselves. But then I would cut that story short in the interest of presenting a second perspective on what we can do with helium nanodroplets, that is, create very hot and rapidly evolving nanoplasmas, which we early on interrogated through spectrometric techniques, but as we speak, coherent diffractive imaging with free electron lasers is not only becoming fashionable, and as I will try and hopefully convince you in this talk, is adding a new tool in our toolbox to interrogate these very fascinating and hot systems. And throughout this talk, I hope to sort of convince this attosecond physics audience, whether now or people viewing it later, that indeed there are many interesting problems with just this one droplet system waiting to be explored through attosecond physics. And what better than this year to motivate exploring helium nanodroplets with attosecond laser pulses, because this is the year for attosecond physics when the Nobel Prize has been awarded for, with I would say, two key phrases. One is attosecond light pulses, and the other being their application to electron dynamics. So this is sort of the current motivation for looking at the dynamical phenomena of electrons, and in this case nuclei too, in helium nanodroplets. But then a sort of if I would say, legacy problem that essentially brings us to interrogate these systems, study and learn from them, is the fact that these kind of radiation-induced phenomena in weakly bound systems such as the DNA, which is hydrogen bonded, abound in nature. And I'm quoting actually a rather old but extremely well-cited paper in Science from about 2 decades ago, where it was evidence that double-strand breakages in DNA can be very efficiently caused by fairly low energy electrons. So this was against the backdrop of a paradigm earlier, or a notion earlier, that it was photons in the X-ray region and others which were scarier in terms of radiation damage. But then we all know that a step into the beach on a sunny day is sufficient to cause a tan. But indeed, it seems that even with UV radiation, there is quite a lot of damage and secondary processes that can happen in biological systems. But then these systems are, of course, so complex that foreseeing and modeling them and a process like radiation damage, which involves a lot of secondary processes, is indeed a considerable challenge. So with this sort of a scenario, it would be ideal to take a host system whose physics we know very well, and put other dopants or other entities into it. Much like in biology, the host is often water, and we have other biomolecules inside, and a lot of interesting photophysics ensues. But then for us, a textbook system from a physics perspective could be to take the simplest solvent, which may or may not be the easiest to create in a lab, but simplest in terms of quantum physics, and then put other atoms and molecules and study the secondary processes which go on. So from that perspective, helium nanodroplets, which are weakly bound aggregates and are nothing but van der Waals clusters of helium, are an ideally suited system to study the physics of aggregate systems exhibiting very quantum behavior. So these helium nanodroplets are extremely cold. I will, in a brief while from now, tell you how we produce them in the laboratory. They have internal temperatures of about 400 millikelvin and a binding energy of a helium binding energy of just 7 Kelvin. And they are inherently in a naturally superfluid state. I'm talking about bosonic helium always, which is helium-4 throughout this talk, unless I specifically refer to helium-3, the fermionic helium counterpart, which we will see just once in this entire presentation. Now, this has been a favorite tool in the hands of physicists and chemists, because these can very easily become, you can say, nanocryoreactors or personal nanocryostats for molecules, because it is fairly easy to attach atoms or molecules or even aggregates of atoms or molecules which are dopants in or on the helium cluster. And they serve as an ideal spectroscopic matrix, especially in the infrared to UV and even vacuum ultraviolet, because helium has a huge transparency window of 20 eV, where one can perform spectroscopy, and they very weakly interact with any dopant atom or molecule, unless we do what we are going to do in this talk, that is activate the helium by photoexcitation. If one doesn't do that and one sticks to relatively modest photon energies, then it's a perfect solvent which hardly interacts with the dopants, or its interaction is the weakest, and it can pick up and cool any atom or molecule. Now, in the laboratory itself, these droplets are produced by supersonic expansion of a nozzle, typically made of copper, with an orifice of typically 5 or 10 nanometers in our experiments, but this is a matter of choice. Some other groups use 20 micrometer nozzles, but all of them, or all of us, essentially maintain a relatively high pressure of helium gas behind this orifice inside this nozzle, where the pressure is maintained typically above 50 bar. And then this nozzle is cooled to below 30 Kelvin. Typically, our operating range is between 5 and 15 Kelvin in these experiments. And out comes from this a jet of helium. It is a high pressure helium gas emanating from this. And owing to the favorable conditions that we maintain, these helium atoms emanating from this nozzle tend to cluster. If the nozzle is maintained at a temperature, let's say, of about 10 Kelvin, then clusters of helium atoms are formed. We can tune the average size of these helium clusters to contain anywhere between few, or typically even few hundred, to several 10 million or even larger number of helium atoms per cluster. Once we form these clusters in the jet that is just upstream of this nozzle, the internal temperature of these clusters is less than half a Kelvin. And if one looks at the phase diagram of bulk helium, then we realize instantly that uh, that less than half a Kelvin is well below the lambda point of helium, where it makes a transition from normal fluid to superfluid for bosonic helium 4. Right? So one could expect that these droplets could be superfluid, but then this is a claim that one has to establish in experiments, and we will see about that in a couple of view graphs from now. But then what emanates is a jet. We essentially take this jet and use a tiny orifice, which we call a skimmer, in order to extract the cold part of this jet, which contains helium clusters, and pass this on to typically a vacuum chamber, which is to the upstream right on my screen, where these can flow over. And if one wants to dope these droplets with a desired foreign species of dopants, then one typically places the dopants, if they are solid, in an oven and heats them to create a vapor. And then the vaporized atoms or molecules essentially stick to the helium droplet with a certain propensity. And then a Poissonian pickup ensues, and we can have a good control over the average number of dopants per helium cluster in this process by changing either the temperature or the pressure of the gas, that is dopant gas, which is present in the doping cell. So this becomes our target system, which are helium nanodroplets with a dopant, which could be anything. It could be a rare gas atom, as I have showed here, or it could be alkali atoms, which at room temperature alkalis are not solids, or it could be alkaline earths. But then the location of a dopant, even a single dopant atom, is typically not in the control of the experimenter. It is dictated by the nature of interaction between the helium atom and the dopant atom. So rare gas atoms and most molecules tend to get dissolved and go into the center of the droplet, whereas alkali atoms are floaters. They essentially attach to the surface of the helium droplet. This is essentially owing to the binding energy of the dopant helium interaction, whereas alkaline earths are subsurface species. So they just lie beneath the surface. So they are sort of snorkeling in the system. And this is well captured in an empirical relation using Ancelotto's parameter lambda. That's a matter of detail. It's just to show that we understand this physics very well. But I must throw in a word of caution here. This logic and this physics holds good for helium droplets, where we do not yet uh, produce vortices and other such structures. If which we do, and they have been done in experiments, then these dopants can also get trapped in vortices. But we are not going to go into those kind of droplets here unless I mention them explicitly. So these are moderately sized droplets with sizes less than about 100 nanometers, and there we know what is going on in terms of the location of the dopant within or on the droplet. So are these helium nanodroplets superfluid? How do we know that they are superfluid, right? So a typical superfluid at the bottom left of my screen, this really iconic sort of image, which is even in the form of a GIF. If you take helium-4 superfluid and hold it in a cup, it creeps along the walls and can drip out of this cup even without this cup being tilted. So this is an iconic image and was really the mainstay of a lot of this essentially gave birth to the area of low temperature physics, right? But then in terms of helium nanodroplet, how do we even know that the helium nanodroplets are superfluid, or perhaps they are not? A beautiful experiment was performed in the group of Jan Peter Tones, and also a companion experiment which I should probably have cited here, but I will mention it in the group of Jacinto Scoles back in those days in Princeton. Here, a rotational spectroscopy experiment was performed with the OCS molecule, and free OCS molecules typically have sharp rotational featured lines. Now, this OCS molecule was doped into a helium droplet, and rotational spectroscopy was done. And in the top panel, labeled A here, where my cursor is hovering, one can see the typical P and R branches of the rotational spectrum, and the lines are really, really sharp, right? So this is the OCS spectrum in helium-4 nanodroplets, which contains about 6,000 atoms. Now, what they did in the experiment was to co-dope this with helium-3, which is the fermionic helium atom. And it was known by then in the physics that these helium-3 atoms sink into the helium-4 droplet and form a solvation shell around the OCS molecule. When that was done under identical experimental conditions, the basically the resolution that they had for the the rotational lines went away because of strong solvent solute interaction. Here now the solute being helium-3, because that forms the solvation layer, and the rotational spectrum was blurred out. The lambda point of helium-3 is not millikelvin, it is microkelvin. In fact, the Nobel Prize to Osherov and Leggett was given for work on superfluidity of helium-3, not 4. And so helium-3 is not expected to be superfluid even at the 400 millikelvin temperatures of the helium-4 droplet. So this essentially proves that this excellent vibrational resolution that one sees in the experiment, which is almost as good as that of free molecules, is due to irrotationality or irrotational flow of the molecule inside the droplet. In bulk helium itself, the analogous experiment called the Andronikashvili experiment was done long ago in the 60s and 70s. So this is the nanoscale version of the Andronikashvili experiment. Now, another feature of superfluids is the existence of a critical Landau velocity. The dispersion curve of bulk helium, this is not necessarily nanoscale helium. I'm not even sure that we know the dispersion curve, measured dispersion curve of helium nanodroplets. Now, in terms of bulk helium, this is the typical dispersion curve of helium. It is the energy versus K, energy on the vertical axis and K on the horizontal axis. And this dispersion curve essentially shows here a maximum, which is the maxon, and this is roton. These are the quasi particles. But the interesting thing to see is that there is a roton gap opening up at about 2 inverse angstroms of k values, right? So this essentially means that there is an energy gap, and if a particle moves with a velocity that is in this region or has a momentum in this region, the particle has a certain momentum and energy range within which it does not excite the liquid, or its energy does not couple to the liquid because there is such a gap. This means below a velocity corresponding to this critical velocity, the a bulk body moving through bulk helium essentially moves through frictionless and without any viscosity, encountering any viscosity. And this, of course, was evidenced in the case of bulk helium. In an experiment performed by the group in EPFL in Lausanne, and simulations done by the Toulouse group, they found a way to do an analogous experiment in nanoscale helium to test the hypothesis of a critical Landau velocity. Essentially, what they did was they took helium nanodroplets doped with a silver atom in this case, and photoexcited the silver atom, and they created Ag star. So a photoexcited silver atom interacts repulsively with the helium host in this HEAG exciplex complex, and essentially the photoexcited silver atom essentially gets ejected out of the droplet, and one can measure the velocity of the photoexcited silver atoms, which is what is shown in the top panel of this view graph as a function of the size of helium cluster into which the silver atom was doped. And one can see that as the size of the droplet increases, the most probable speed with which the silver atom is ejected is kind of reaching a nominal value, which is a little less than 60 meters per second. In bulk helium, the critical Landau velocity is 60 meters per second. So this group, they not only measured the exit velocity or ejection velocity of individual silver atoms, they did it for nitric acid, for TMA molecules, and a host of other organic molecules whose names I can't even expand, but it's evidence the number of letters essentially shows that the size of the molecule is growing. It's an organic chain, right? But all of these very nicely fall onto a particular velocity. So this evidences that there is something like a critical Landau velocity even on nanoscale. Of course, there are possibly even other details to be considered, and this is still a matter of discussion, but it starts to behave like a superfluid, or there is a strong evidence that this is a superfluid, and hence even a condensate in itself. Coming back to the experiments that we do, in our experiments, as I informed you, we produce helium clusters or nanodroplets, here by expanding helium gas through a nozzle. It passes through a doping cell, picks up the dopants. In these experiments, we shine a focus synchrotron beam onto the helium cluster and ionize these droplets. And these the ions and electrons, which are our photofragments, can be efficiently detected using a couple of spectrometers operating in tandem. On one side, to detect ions, we have a time of flight mass spectrometer, which is in the Wiley-Maclaurin configuration with electrostatic lenses, and we time focus the ions on a microchannel plate detector. On the other side of this spectrometer, in this case the bottom side, we have the photoelectron spectrometer, where we essentially measure, we do so-called velocity map imaging, which I will describe in the next graph as to what it is. So, but then the important thing in our experiment is we do photo-ion spectroscopy and photoelectron spectroscopy in coincidence. So if I just run this simulation once again, here the fragments are formed, the photoelectron goes and starts the clock, and this clock then tracks the time of arrival of the ion at the detector. The flight time of the electron is in nanoseconds, and that of the ion is in microseconds. As a consequence, it is easy to use the electron as the start of this clock and measure the flight time of these ions. And if we do this one after another and collect all the ions, we form a time of flight signal where the horizontal axis is arrival time and vertical axis is the counts, the number of electrons that arrive at a particular time. The arrival time of the ions is proportional to the square root of the charge to mass ratio of the ions, and as a consequence we can identify ions based on their flight times, right? But what about the electrons themselves? On the other side, we had the electron spectrometer. Electrons are too fast in our case to detect by time of flight. With developments in electronics, this is even becoming possible. But in this case, we don't need any arrival time of the electrons. What we do is we essentially project the cloud of, the sphere of electrons that come out from this photoreaction. They essentially live on the surface of a momentum sphere, depending upon which direction the momentum vector of the photofragmented electron points to. And then once again, using a careful set of electrostatic lenses, we project this onto a position sensitive detector, which is over here, and form a map of the velocities. We essentially project the Newton sphere onto the position sensitive detector and get a map of the electrons arrival. Electrons with zero transverse velocity would have arrived along the transverse axis of the spectrometer. Electrons with non-zero transverse velocities perpendicular to the axis of the spectrometer would arrive off-centered. But then, owing to the symmetry and the geometry of this problem, we can inverse transform or inverse Abel transform the map over here in order to reconstruct the momentum sphere. In our experiment, we operate this in tandem. That is to say, for every photo ion, we can essentially get a map of the photoelectron that is born along with it. But one can also imagine that in these photofragmentation processes, we could have multiple ionizations happening, in which case we would have 2 electrons and say 2 parent ions, or we would have 3 electrons and 3 parent ions. This technique can be used in order to basically figure out both the parents in the case of a 2 electron 2 ion process, as the case may be. So this is also something which will become important in the remainder of our talk. But then let us see how this works out in action. So if I take a simple atom such as a helium atom and photoionize it with a single photon, then and I can measure the photoelectron angular distribution using the velocity map image. That's how it looks like. It is 2 moon crescents, one on top, one at the bottom. So this is basically atomic physics 101. The angular distribution of photoelectrons from an atom when it's a single atom process is essentially having an angular distribution of 1 plus beta times cos theta. For atoms, beta has a value 2. Now, in the case of droplets or clusters, the photoelectron which leaves one of its parent atoms doesn't just come off towards the detector. It can collide on its way with neighboring atoms, and therefore the beta that one measures in the case of helium nanodroplets of clusters can be close to 0. One still sees these crescent-like features over here. That is simply because in the same jet where helium clusters are present, there is also a considerable fraction of unclustered helium atoms. So, but then one can make quantitative differences between atomic helium's photoelectron angular distribution and that of helium nanodroplets. This is sort of a warm-up to looking at further VMI images in this talk. In the case of helium nanodroplets, we started out with experiments where we took 25 eV photons from a synchrotron and ionized helium nanodroplets. In this case, they were doped with lithium, so we see also lithium plus ions. But please ignore that for a moment. Essentially, the important lesson to pick up from this time of flight mass spectra is that when we ionize helium nanodroplets, the most prominent ionic product is the helium dimer ion. It is not necessarily monomer helium ions. We see helium monomer, we see a lot of helium dimer, and we see a bit of helium trimer ions too. There is some water vapor always present in the background, which also shows up in the mass spectrum. So this is VMI. So corresponding to these parent ions, we can measure the photoelectron angular distributions, which is helium plus, helium 2 plus, helium 3 plus. These are some early photoelectron maps which we recorded in 2013 in initial experiments, which Dominic, me and Marcel did with colleagues at the synchrotron. So we have the ion TOF measurements, time of flight is TOF, as well as correlated photoelectron VMI measurements. So let's see what more we can learn from in this process. In order to figure out the electronic structure manifold of helium clusters, it's not enough to look at photoelectrons and photoions, even if we do them in coincidence. We also need to look at the other complementary process, which is fluorescence. That is, if I excite helium clusters at various photon energies, what about radiative decay and relaxation of the system, right? So atomic helium has this energy structure going all the way from 1s2 to its excited states to 2p, which is the first dipole allowed. But in droplets, we can also have electrons going down to what is atomic like 2s states. But then we have the other dipole allowed transitions, 3p, 4p, and so on, all the way up to the continuum, which for atoms is begins at 24.56 electron volts. But then if I excite helium droplets, for example, at photon energies all the way from about 20 eV up to 25 eV, I see a fluorescence spectrum which looks like this. This is from the work of Thomas Moller's group, which is Jopian and others. And this essentially gives us the electronic structure of helium nanodroplets. And based on these two pieces of information, that is photoelectron photoion coincidence spectroscopy and fluorescence spectroscopy, we can form the full picture of what happens to EUV photoexcitation and photoionization of helium nanodroplets, which is as follows. Here I'm showing the fluorescence spectrum in the right side panel, and on the left I'm basically having the photoionization curve. I increase the photon energy all the way from 20 to 26 eV and plot either the yield of electrons or the ions, total ions, all the ions that I can record in my spectrometer, and also particularly helium dimer ions, which are a droplet specific signal. This helium dimer signal comes specifically from helium clusters alone. So what we see is that as we go from 20 eV onwards, we first see a region where just excitation happens. There is no ionization because we don't see any signal of electrons or ions. But the fluorescence spectrum over here shows a very sharp band, although I have rotated it vertically in order to present it like the density of states. And then the ionization of droplets starts to happen from 23.1 eV onwards. So this is a region which is a sort of intermediate region to direct ionization of atoms inside the helium droplet by the photons, as they would in the case of atoms also. So we can basically demarcate three regions of photon interaction with helium atoms in terms of a single active electron picture: an excitation region, a direct ionization region, and an auto-ionization region, which is in between, which is also very interesting. But in this talk, we will probably not see too much in terms of the details of this. Now, what about the dynamics of the photoexcitation of these droplets in the EUV regime? A beautiful experiment was performed by Marcel Mudrich and others. I was not a part of this effort. But then this experiment is really a benchmark and must be, in my opinion, cited in every talk. And essentially, they took XUV or EUV radiation at the first dipole allowed transition corresponding to 1s2p of atomic helium, and photoexcited the helium droplet. So an atom, after absorbing the 21 eV photon from the Fermi free electron laser, which is a pulse source, the pulse duration is about, I think, a couple of hundred femtoseconds, is excited from helium to helium star. And in this experiment, they did a form of depletion spectroscopy, not depletion, sorry, photoelectron spectroscopy. So the probe pulse was an ultraviolet probe, which is coherent. Essentially, Fermi is a seeded FEL. The Fermi FEL produces the 21 EV XUV photons or higher energy by essentially converting these primary optical femtosecond pulses using a high harmonic generation like process, the HG process. And these two pulses are extremely coherent and very well time synchronized, but for a little bit of timing jitter, which I think is of the order of maybe few 10 femtoseconds. but not more. So then the pump pulse excites the system, and let's recall the electronic manifold of atomic helium and the density of states in helium droplets. So when the XUV pulse comes, it excites the ground state, the droplets from the ground state to this 1s2p band of states. Now, that's essentially it. It triggers the dynamics. What can typically happen is that in this case, they chose an energy so that the electrons are excited to the top of this very nice band, which corresponds to atomic 2p like singlet excitation. Now, there is a possibility that after this excitation, typically as it happens even in a lot of condensed matter photo excitation studies, there can be an intraband transition in which the electron can essentially relax down to the bottom of this band. The bottom of this band essentially has the 1s 2s atomic like states. For helium atoms, 1s 2s is a metastable state. This we know, right? So we can foresee a bit of the dynamics that's going to happen if such an intraband relaxation happens. But then in this experiment, in the spirit of pump probe experiment, you use a probe pulse and create a signal that essentially emanates against a background which is nothing unless the probe pulse interacts with this atomic these nanoparticles, which is a UV probe pulse of about 4 eV. And using this UV probe, this excited helium star atom is ionized further, and the photoelectrons are measured when they come out into the continuum, and the energy of this photoelectron serves as an excellent experimental parameter for this pump probe experiment. This is the style of experiment done in a whole lot of attosecond physics experiments too, such as rabbit and other techniques. So in this experiment, what did they see? So Masel and others saw essentially that once after the probe, essentially when after the pump, when the probe pulse essentially interrogated the system, there is a phase in which there is a fast decay taking place from, so that the electron that was excited to the top edge of this 2p band relaxed to states that essentially are formed more due to the coalescence of atomic 2s like states. And then the dynamics essentially followed, where the 2p of the droplet essentially decayed down to these 2s states, and the system lived there for quite a considerable amount of time. They've recorded this in this case up to 2 picoseconds at least, but it typically lives even longer. And this, for the purpose of this talk, is an important aspect. So let's move on from this. And there is a very interesting detail which I will not spend too much time on. But then in helium droplet physics, it is known that this excited helium star, which is essentially helium with a very loosely bound electron, is inside the droplet in the form of actually a nanobubble. Basically, the interaction between the excited helium and the neighbors is repulsive because of the Pauli principle. So there is a cavitation happening around the excited helium. This is a density functional theory calculation carried out by Manuel Barranco's group in Barcelona, and they basically perform this quantum mechanical calculation, which clearly shows that this is in the form of a cavitation bubble, and essentially the helium atom can even get ejected out of this droplet due to the repulsive interaction. So there is very nice physics going on the nanoscale in terms of spatial dimension and in terms of temporal dimensions. In terms of it is on the femto-picosecond time scale. So this is in some sense showing us how versatile a playground helium droplets are on the femtosecond time scale. Now, having had a good idea of what happens to single electronic processes and the fact that they can themselves be very intriguing, let's come to now the mainstay of this presentation, which is correlated dynamics in helium droplets. Helium is basically the textbook two-electron system, which people like to study a lot, and a lot of even coherent control attosecond experiments have been done, especially from the group of our collaborators, Thomas Pfeiffer and others, a whole series of nice experiments. But then all of this is rested on the bedrock of a Fano resonance in helium of this textbook two-electron system, right? In the case of atoms, we have this very typical Fano profile when we go up into the doubly excited manifold and the Rydberg series that leads all the way from about from 45.8 eV up to the double ionization of the helium of atomic helium. We see these very nice series of Fano lines. This corresponds to the atomic 2s2p, 2s3p, and so on for atoms. That's the black curve. Now, purely out of curiosity, we performed the same experiment on droplets at a beam time which was proposed and led by Aaron LaForge at University of Connecticut. And in the measurement with helium droplets, we see that these Fano structures survive, and that's probably the first lesson that we learn, although they seem to be distorted or broadened in the process of merely due to the fact that this belongs to the cluster and not individual helium atoms. So we performed systematic measurements taking the intensity of the photoelectron signal as our measurable parameter, and looked in detail at the shapes of the Fano lines for various droplet sizes, all the way from 5 atoms per droplet down to about 2 million atoms per droplet. And one can see a sort of systematic movement of the width of these spectral lines. Yet the Fano shape and characteristic does not vanish at all. And we reasoned in this Fizzed Away paper that it is the participation of these molecular states of the helium star exiplexes involving more than one helium atoms, and the density of helium atoms in the droplet, which is essentially flat towards the center, but then being a sort of fluid-like system, does not have a sharp boundary. It essentially tails off rather gradually in the helium droplet. So this tends to explain this structure, but I would certainly like to believe that there's a lot of two-electron physics that is playing out in terms of details in the system. And in fact, this is also worth some further pursuit in terms of possibly time-resolved experiments on the attosecond timescales. But then let's dive deep into the secondary processes following the photoionization of helium. Let's take a very heuristic picture over here. What would happen if I consider a photon of energy of greater than 45 eV, and it will become clear why I'm talking about 45 eV here. And such a photon essentially impinges on a helium droplet. This, of course, will create an electron, an unbound electron released from its parent atom, and leaving behind a helium plus ion and the electron itself. This electron will, of course, tend to escape from the droplet, but in the process, it can collide with one of the helium atoms in the droplet. Essentially, the ionization energy of helium is 24.6 eV for atoms. So the photoelectron that comes out of this should carry an energy of at least 20 eV. A 20 eV electron can electronically excite a helium atom in the neighborhood by electron impact excitation. So this is the excited helium atom. And finally, the electron comes out in the continuum, and one can measure these as photoelectrons with kinetic energy, that is h nu minus the IP of helium minus the excitation energy of exciting one of the atoms in the droplet from He to He star, right? So this is a basic heuristic picture. Let us take this forward and look at what happens in an experiment. So we picked up helium droplets initially of a rather small size, that is 2 nanometers, and used 55 eV photons to do photoionization experiments and measured the kinetic energy of electrons using the VMI spectrometer. As I mentioned earlier, in the VMI spectrometer, all photoelectrons of a given kinetic energy, which is essentially speed, but emanating at different angles, will lie on the circumference of a given circle. So the radius here is proportional, radius of the circle is proportional to energy. Therefore, this is a straightforward readout of the velocity of the electrons, which is why it is called velocity map imaging, whereas kinetic energy is the square of velocity, and we will also be able to extract electron kinetic energies from this after doing some procedures like Abel inversion. So we record, in the case of small droplets, a ring-like structure. Let's call this structure A. Now, As a curious experimenter, I increase the size of the helium nanodroplet, again keeping the photon energy the same, 55 eV, and once again do the VMI map, that is record the velocity map. This velocity map now has actually three features. The feature A, the outermost ring in the VMI. So we are getting comfortable with reading VMI images and mentally converting them to some kind of spectra. But it's a good instinct to have, especially in the lab and during an experiment. But then we see over here a structure called, which I call the ring B, getting formed over here. It's interesting. There is also a dot at the center, which is very low kinetic energy electrons, which is an interesting feature in itself. But I'm not going to discuss that in this talk. We can possibly do that if one has questions. But let's ignore the center for the moment and acknowledge the fact that there are two features, A and B, corresponding to electron populations with two different kinetic energies. So what are these? It's not very difficult to figure out that the fastest electrons are the electrons that come out maybe from surface ionization. They come out with the highest kinetic energies without any inelastic scattering from helium atoms. They just escape the droplet almost untouched. Whereas these electrons forming the feature B essentially are the ones that I described in the previous slide. So these come out with kinetic energies of h nu minus Ip minus the excitation energy of helium. And this is the second feature. Now let's do a systematic study of electron energy maps using the VMI technique and increase the droplet size even further. Let's go from 5 nanometers to 40 nanometers to as far as our experiment could allow then, which is about 50 nanometers. Now for these 40 and 50 nanometer droplets with containing about 5 million or 10 million helium atoms, these velocity map images that we see here have, apart from this reference center feature, which I request you for the time being not to pay too much attention to, three rings. Ring A, which is due to the direct process, ring B due to one inelastic scattering event, and an intermediate ring C. Right? So this is curious. Where does this feature ring C come from? Right? So the rest of this section of my talk is centered around talking about this. So we have three features A, B, and C as I showed. We can take the VMI image and convert this to a photoelectron spectrum. Right? We came in with 55 eV photons. So the direct ionization results in photoelectrons with kinetic energy of 55 minus the IP of atomic helium, which is about 25 eV. So we have this 30 eV peak. The inelastic scattering peak is at about 10 eV, but then this intermediate peak C appears at electron energies of about 16 eV. So now we performed, as I said, collected these spectra for various droplet sizes from 700 to several 10 million, and the droplet size is changed by changing the temperature of the copper nozzle in the experiment, right? But where does this mysterious feature C come from? That's the question we set out to answer. It took us quite a while in order to figure this out, because we essentially wanted to, understand this new process from many of the things that can go on in clusters. So this feature, the feature C at about 16 eV feature, it turns out is an ICD process, which I will spell out very quickly and shortly in a slide that is to come. But where does this feature come from? Let's try and understand this from an energetics perspective. So what is happening in the droplet here is that after the initial photoionization, an electron inelastically scatters from one of the neighboring helium atoms, in the process exciting it and creating a helium star. But in the process, this photoelectron essentially is hovering around in the droplet. But then there is the positively charged ion in whose attractive potential the electron exists. And some of these electrons essentially, in the process of scattering further elastically and still losing further kinetic energy, are continuously drawn back towards this ion, and they recombine. When they recombine, they form a second helium star in the droplet. So now at the recombination process, they have a helium star and another helium star that was created due to the inelastic scattering process. And this could also be an exciplex. It could also have combined into a helium dimer star, an excited helium dimer molecular excited species, but whatever it may be, now we have two excited helium atoms, oligomers in the process. These two excited helium atoms can perform some motion in the droplet because their interaction with the neighboring atoms actually is repulsive. And we have reasons to believe that they can even migrate towards the surface, coalesce, and interact with each other. So in the process of this kind of interaction, we have essentially energy transfer processes happening. And this leads to the following type of interatomic decay process. The process of all this elastic and inelastic scattering and recombination was modeled using Monte Carlo simulations, but I will skip that in the interest of time. So what is giving rise to this intermediate feature in the photoelectron spectrum? The really interesting one is the following. We come in with a photon, remove a photoelectron, put it into the continuum, and this electron essentially after an inelastic collision and exciting a neighbor helium atom recombines with its parent ion in an excited state because that orbital is geometrically and cross-sectionally larger. And these two guys then collude with each other in an interatomic Coulombic decay process where it is helium star if it's two atoms, or it could also be an excited helium dimer participating in the process. And then the ICD process happens wherein one of the excited electrons one of the electrons close to one of the excitation centers decays to the ground state, and that energy is transferred over a considerable range of distance, and the other electron comes out of the droplet. Of course, the closer these two atoms are, the greater the overlap of the orbitals and greater the interaction and higher the propensity of the ICD. But there is favorable nuclear motion happening in the droplet among these excited species so that this becomes a dominant ionization channel. So a correlated interatomic decay, interatomic Coulombic decay driven by recombination is what drives the physics of secondary processes in helium nanodroplets. And this was the mainstay of our recently published FISREV letter, in which we worked with this wonderful team from in Bean Times led by Marcel and sub by me, and at the electrosynchrotron, and then at some really high resolution experiments performed also at the Astrid synchrotron, and it has been an effort for a few years, right? So we have essentially the key to this ICD process is essentially the realization of two excited helium star monomers or oligomeric ions which take part in the process. So we not only did the photoelectron spectroscopy of the system with the conventional velocity map imaging spectrometer, we did high resolution spectroscopy using a hemispherical analyzer, the results of which I'm showing in the bottom panel B. And indeed, with the high resolution spectrometry, essentially the high resolution spectrometry is a zoomed in version of a slice of one of these ICD peaks. We were able to clearly assign the atomic and molecular states that are involved in this process, the greater details of which can be found in our paper. We also realized and acknowledged that we could have processes in which, owing to the large size of the droplet, two photons could have been absorbed by the droplet, so that you have two ionization events happening in the droplet, and you also have two recombination events happening. But again, in the two recombinations happening, you essentially could have a helium star and a helium star being formed, and an ICD following thereafter, right? So in one sense, in the true spirit of this talk, I would like to maybe sort of motivate the fact that these experiments could be time resolved. This is really fast dynamics happening in the droplet, or even on few femtoseconds or few 10 femtosecond time scales. So therefore, attosecond probes would indeed be an excellent choice for performing time resolved experiments, and these are all single photon XUV processes, right? As a consequence, one could even do this with tabletop high harmonic sources. Now, there is another nice experiment performed using the Fermi FEL, and a different type of ICD process where two XUV photons were absorbed by a helium droplet. In this, there is no recombination required in order to create the two helium stars. It was a two-photon absorption induced by a strong XUV pump pulse. This was a beam tank led by Aaron Laforge and Marcel Modish, and I show this because it's a beautiful experiment where the femtosecond timescale physics of the ICD process was resolved. So again, in the interest of time, let me not go into the greater details. The bottom part of the time-resolved kinetic energy spectra is what I had shown earlier already, whereas the top panel is the time resolution of this direct of the ICD signal arising out of direct photon excitation for two heliums to go from helium ground state to helium star and leading to an ICD. Of course, one could have desired a much better statistics, but then these beam times last just for a couple of days at the very competitive Fermi FEL. And even from this, the signal, they discerned the temporal dynamics of this, and one can find the details of this in this PhysRevX paper. Let's move on from this after noting this very interesting fact. I would just want to show this 10-second simulation of the nano bubbles which are created in helium. So these are the two excited heliums. As I said, there is a cavitation around the excited helium stars, and one can see this is essentially DFT of helium atom DFT, which was performed by the Barcelona group. And this shows some very interesting molecular dynamics of these two excited helium atoms in the droplet, leading to the atoms eventually sort of, the two cavitation bubbles coalesce almost as we see in bulk fluids, and then ICD happens. So this is the physics of these systems is very rich. Now let us, I would like to close this presentation in the next five plus minutes by motivating collective electron dynamics processes in helium nanodroplets. So this is a sort of part 2 short story of this presentation. Now we move on from excitation with a weak single photon excitation to strong excitations, particularly using intense near infrared lasers, or it could even be intense extreme ultraviolet pulses from an FEL. So the physics that we can expect to happen when intense pulses interact with helium clusters is the following. Whatever be the pulse, here is a nanometer sized target particle. An intense pulse comes, ionizes this target rather heavily during the pulse, creates a rather hot plasma, which we call the nanoplasma. This nanoplasma is also heated by the pulse. It really can have huge temperatures, much hotter than even astrophysical temperatures. And after the pulse is gone, this system essentially relaxes as Coulombic and hydrodynamic pressures make these hot nanoplasma balls expand, and the charge density of the system is diluted. Finally, they undergo Coulomb explosion and disintegration. This entire process can actually happen on extremely fast time scales, as we realized in experiments. So these timescales could be anywhere from the range of few femtoseconds, but then the dynamics can last all the way even to several nanoseconds. So motivated by the fact that we have a very rapidly evolving complex system, we performed coherent diffractive imaging experiments using these nanoplasmas as worthy targets for rapidly growing free electron laser technology. In our experiments, we essentially took once again a beam of doped helium nanodroplets, in this case doped with xenon atoms, and then we focused a near infrared, sufficiently intense near infrared pump laser on at these helium droplets and created a nanoplasma. After a delay of some delta t, typically half a picosecond or all the way going up to a nanosecond, a delayed XUV FEL probe with a wavelength of 5 nanometers is spatially matched with the near infrared laser, and the probe pulse scatters of the nanoplasma, and the scattering pattern is recorded on a very efficient PNCCD camera. So the pump ionizes and ignites the nanoplasma, and the probe scatters off from this rapidly evolving nanoplasma and produces a scattering image, thus giving a lot of information about the instantaneous state and the spatial structure of this of the nanoplasma. Since nanoplasmas will do disintegrate and the charges can be collected and measured, we had a VMI spectrometer working in tandem. So in this case, again, it's a sort of pulse to pulse coincidence imaging and spectroscopy with the VMI, although the spectroscopy was not that useful in this case. And we could do correlated imaging, photoelectron imaging and X-ray scattering in this experiment. So these experiments are enabled by extremely impressive detectors, which allow us to and free electron laser pulses, which allow us to essentially capture a coherent diffractive image, which is a scattering pattern from a single FEL pulse. We are able to collect enough scattered photons that we can do some reconstruction, and this entire process of an FEL pulse scattering of the target, producing a scattering image from a single pulse, and then our ability then to reconstruct the image constitutes coherent diffractive imaging, which for us was the probe in these experiments. And what did we see in the experiments? This is work in progress. So at zero delay, which is almost at the time when the infrared pulse is going to ionize the nanoplasma, these are coherent diffractive images of the neutral helium droplets. Well, the quality of our images was compromised by a lot of parasitic scattering from various parts of the chamber and things, and the bottom half of the detector was unusable during this experiment for other reasons, but then we can still endeavor to reconstruct these images. So these little rings which we see here are the diffraction rings. So now 1 picosecond after the near-infrared pulse has interacted with the helium cluster, we still see some diffraction rings. At 3 picoseconds, they've almost disappeared. There is only a little bit. At about 6 picoseconds, we have some rings too. We should understand the fact here, and I should disclose that at all different delays, we don't have droplets of the same size because we are sampling the size distribution of the droplets. So that does play a role. But then broadly speaking, these ordered ring-like structures essentially give way at about 500 picosecond to to specular structures in the diffraction pattern, and this tells us that the nanoplasma is disintegrating. So right now what we are doing is to do the following. We perform what is called forward simulations. We estimate the size of the helium cluster and the dopant plus xenon dopant, which forms a cluster inside the droplet from the conditions of our experiment. So we take scattering images which are like this, and then we use the Condor platform to perform simulations. We place essentially the 20 nanometer dopant cluster at different locations inside the helium cluster and produce scattering patterns using the 5 nanometer X-ray photons as it comes from the FEL. And we have essentially been able to figure out that the various ring patterns which we see all the way from undistorted rings to rings with certain angular streaks of various frequencies which are present, all these can be sort of in a way fitted to the various locations of center of the xenon cluster inside helium droplets of various sizes. If we had much better quality CDI images, we could have done a more direct inversion, but here we are doing a little bit of intelligent guess, but based on sound logic, using the inversion platform to figure out the state of the droplet. And as I showed you, as the nanoplasma evolves on a nanosecond time scale, picosecond to nanosecond time scale, these scattering patterns become specular. So even these can be inverted using the same form of algorithm. This is work in progress. Keshav is taking this up with a lot of enthusiasm, and we can figure out that in the inversion over here, the droplet has disintegrated to even further smaller clustered chunks of helium, and we will take up this further and try and learn the story of what's happening to the life of a nanoplasma all the way from a couple of hundred femtoseconds to much longer. And to give you an idea of what is happening here is a molecular dynamics simulation, which if it runs, I think it's unable to run this file on my computer at the moment. So let me skip that. But the message here is the following, that these nanoplasmas can evolve on a fairly rapid time scale. So this was an experiment that I did long ago, where we essentially took 10 femtosecond pulses, really, really short pulses, and this is a single pulse experiment. And at the intensities of our interest, all the way from 1 to 7, 10 times 10 to the 14, these are near-infrared 800 nanometer pulses from a titanium sapphire laser, without any doping, that is zero number of doped atoms, pure helium droplets are not ionized by these intense femtosecond pulses at all. Okay, the duration of the pulses is 10 femtoseconds, whereas these helium clusters, which contain about 10 to the 4 helium atoms, can be driven from being entirely transparent to these pulses to a charge state where the charging of the droplet is entirely saturated by adding just about 7 xenon atoms as seeds. So all of this is happening within 10 femtoseconds. So this is a few femtosecond process. This is the rapid dopant-induced ignition of these helium droplets. This form of dramatic change in the characteristic of this droplet and creating the nanoplasma is indicative of the fact that there must be a resonant phenomenon underlying this. And I should give credit to Alexei Mikaberidze and his companion paper, which we cite in this work, where they showed that the morphology of the nanoplasma leads to a resonant interaction between the driving laser pulse and the droplet. Also, there are charge transfer processes which are happening inside. Whatever the case, the interesting thing is within an otherwise neutral nanodroplet on a few femtosecond time scale, a nanoplasma which in this paper claims to have a cigar shape evolves, and the morphology drives the system into a very ionized ignited state owing to this dopant-induced ignition process, which happens on a few femtosecond time scale. Therefore, as free electron lasers, especially such as the LCLS and possibly EUXFEL, but I think LCLS can produce even isolated intense attosecond pulses. So these open up doors to do even attosecond timescale CDI imaging. And for such magnificent tools and machines, worthy systems that can indeed test their abilities are important. And nanoplasmas and helium nanodroplets could be one of those positioning themselves as worthy systems. With that, I would like to come to the close of this seminar and emphasize the fact that there is not only plenty of room on this nanoscale, but there is also plenty of time at the bottom. With that, once again, I'd like to thank you for your attention and the Atto Fridays team for this opportunity. And I can take questions now.
So thank you very much for this really nice talk. Other questions, comments? I can see there is one, but if you would like also to raise your hand, feel free to do so. One thing that we are very proud is that Atto Fridays is a very international endeavor. So after the questions, we're going to look at this poll. But from time to time, we launch one to know where people were joining from. And typically, we have people from 3-4 continents watching. We have a question here from someone who is an anonymous attendee. Please explain the low kinetic energy electron in slide 27. So you need to see what slide 27 is. Anonymous, if you like, let us know who you are and we allow you to speak. Otherwise,
so the low energy feature essentially was first observed by the group of Dan Newmar. So these low energy electrons are formed due to the participation of molecular states in the helium droplet, and this is also a consequence of a lot of scattering of the electrons, photoelectrons that are emitted from the droplet, which I don't know if I'm sharing my screen at the moment. Am I?
No, you're not. You're not.
Okay, sorry. Maybe, okay, that I should do. Now is it visible? Yeah, okay. Yes, there it is. So essentially, this low energy feature is what the question is about. So here, this is an intriguing feature, and basically the electrons which come out of the helium cluster can also undergo a lot of elastic scattering and lose energy. And there are the molecular Xc plus states. Van der Waals molecules of helium 2 star of that type are also formed. As a consequence, the electronic structure is a pretty rich feature, and in this case, all of this goes into the formation of these zero kinetic energy electrons. One of the things that I must admit is that these are not extremely well understood, owing to the fact that spectrometers that are that we have are not yet having. I mean, we need to really high resolution spectroscopy to discern any spectral features over here. So, in that sense, we have a broad understanding of where these come from, but then in terms of details like what are the molecular states that are involved in the entire physics, that is still work in progress. Carla, I think you're
You
muted.
did, yes,
Oh
yes.
yeah,
Sorry.
yes.
Thank you. Are there further questions? I'll share the poll. You can see that today we have a lot of people from Asia, as you can see, but we still have Europe, Asia, and US and Canada. So, as usual, people from across the globe. And we had, or at peak time, 11 people following YouTube. So,
Mhm.
wow, really enjoying your talk. Um, would anybody like to ask? We have another one. No, this is one is done for questions. Now,
Mhm.
I have a question for you said you like to talk to the general public. At the very beginning, you mentioned that there's interest in these droplets because people are also interested in understanding biomolecules and DNA strands. I know
Yeah.
this is still a bit in the realm of science fiction, but maybe you could tell us, the public, what uh, what would be the perspectives on that and
Yeah.
specifically how this fits in.
So essentially, of course, I'm not an expert in radiation damage or therapy for that matter. But the whole point, if I may go and pull up that slide to present a context for the discussion, is the fact that um, when we have photons or electrons interacting in a biological system, the primary event of ionization or excitation itself is somewhat obvious to guess, which is why the whole process gets triggered off. But then the challenge lies in figuring out all the secondary processes that ensue, which essentially contribute to efficient damage, which could be good in some cases, such as radiation therapy in terms of therapeutics, or in other cases, it could be something parasitic, right? So, one in all these scenarios, for example, there are problems of determining the right amount of dosage for doing therapy and or even imaging, right? Where radiation is used. In all these, one needs to essentially build suitable models that can essentially figure out how many grays of radiation can be used in the process of irradiating, whether it's people or whatever else. So secondary processes hold the key for us to build these models. And what typically happens is, owing to the complex nature of the molecules, and all these are quantum mechanical entities, even doing an atomistic simulation, as in the case of atoms, molecules, or even small clusters, in terms of discerning all the secondary processes becomes challenging, which is challenging even for the reason that these are weakly bound aggregates. There are hydrogen bonds, and these are not covalent molecular bonds, or it's not even like metallic bonds in terms of metallic clusters and so on. As a consequence, even to stabilize a structure once the photoexcitation happens becomes pretty challenging. So even in the case of these well-known ICD processes, this is the challenge. So there we have also done some experiments on the ICD process. For example, in the case of doped helium clusters, we recorded. I really kept out the doped helium droplets in the interest of time. In the case of doped helium clusters, we can do similar experiments where we basically scan the photon energy and just measure the yield of the dopant ion. And we actually know that there are two kinds of processes happening. One is an excitation transfer process where we excite a helium cluster so that we go from ground state helium to helium star. And if we had an alkali atom attached to the droplet, the alkali atom would very efficiently get ionized due to an excitation transfer from helium star to the alkali. If we had a rare gas atom, essentially the red gas atom gets dissolved into the droplet. The red gas atom essentially gets ionized in a secondary process by charge transfer. For alkalis, it's excitation transfer. For rare gases, it is charge transfer. So even for a very simple textbook case where we take two different kinds of atoms, the details of the secondary interaction becomes important. Now, we further understand that this excitation transfer or the penning process is a type of ICD process that is going on in these systems. However, when it comes to doing theoretical simulations, let's say we take two helium atoms and we want to make interact, we form like a three atom system, two heliums and say a lithium, right? And then you shine a 21 eV photon on the system and want to model this or simulate this system, right? A lot depends upon the separation between the helium bond axis and the lithium, right? So even determining these kind of stable structures to do the calculations is non-trivial. There are only few people around who can literally do this, which essentially all boils down to Lenz Sederbaum and his legacy, for example, right? So in that sense, of course, apologies if I'm missing out anyone else important from mentioning, but it's a very small community of ICD specialists who can do that, right? So this essentially tells us that these secondary processes become challenging even in these textbook systems. So when we talk about really complex systems that take us into biology, it certainly is a combination of theory and experiment that needs to go hand in hand. So colleagues have taken the nucleobases, the ATGC bases, and put them in helium droplets and have started doing, let's say, photoelectron spectroscopy. The merit of the helium system also comes about from the fact that now I can create. Helium is not a good solvent. Biology doesn't happen in helium. It happens in water as the solvent, right? But then helium droplets provide this very nice avenue that I can take, say, maybe a nucleobase like adenine, guanine, or whatever, or it could be some a good substitute for them, a molecule like THF. Now put that and co-dope the droplet with this molecule of interest and water, and then study the secondary processes, right? So that would be really, really, really interesting. So we can form bio-like aggregates, and which is something we would also like to do, and perform photoelectron spectroscopy of these systems. So using helium droplets as a matrix for spectroscopy would be a way to systematically build, hierarchically increase the complexity of these systems and study them and further our understanding of more realistic systems, which could aid our understanding in terms of going down to quantum mechanical atomistic details, yet getting insights that are relevant for photobiology.
Thank you. We have also a question from Sarang Basne. Since helium nanodroplets are the primary focus of the studies, are there other systems or materials that are also studied in similar investigations? What factors contribute to the selection of a particular system in these studies?
So, Sarang, if you're on Zoom, you could even pose your question by voice, but even otherwise, if I get your question correctly, are there other systems and materials that are... Yes, there is a lot of work done on other clusters that one can, form in free jets, and a comparable system would be free jet clusters, where we essentially take nanoparticles and fly them in the experiment and interrogate them with the laser. So this is in contrast to experiments where you can, in some cases, if the structure is stable at room temperature, one can deposit them on a substrate and study them. In which case, one has to work hard to disentangle the substrate effects from that of the particle, but then one can never really get rid of the particle surface substrate interface. So free jet cluster experiments are the cleanest, so we sort of prefer to do them. A whole lot of work has been done with rare gas clusters, but also with water clusters, with micro droplets of water. That's another beautiful area of study. We also did a couple of beam times on that, and in fact, we formed aggregates of water clusters inside droplets and studied their fragmentation physics following photoexcitation. There is a whole series of beautiful experiments done by electron impact ionization, particularly from the group of Paul Schreier in Innsbruck. So our imagination is the limit. We can study more or less any kind of system in these flying droplets, various clusters, various preset nanoparticles. There are experiments on silica nanospheres used to study. They are coated with, say, molecules, and one can again do optical spectroscopy, photoelectron spectroscopy, and all of the forms of spectroscopy. One can definitely do core and diffractive imaging at free electron lasers. People have put little viruses, but not the ones that are harmful, but this typical Mimi virus, and gotten a single shot diffraction image and reconstructed the structure of the virus. So things like that. But all I'm trying to say is that anything that can get into a jet and one can have a sufficient target density of, one can study those using similar techniques. So it's really an invitation to explore these kind of systems.
Hello, Professor. Hello, everyone. So,
Hello, hi,
following
Sara.
the question that you
Yeah.
mentioned in your presentation that you had also used silver particles in the helium systems. So, were there any other nanoparticles as well, like similar, like silver?
Yes, so the work with the silver atoms was not done by us, but by the group of Marcel Drabels from EPFL. But yes, they doped with silver. One could essentially vaporize other metallic precursors in an oven. We have studied alkali atoms attached to helium droplets, like cesium, like rubidium, sodium, potassium, and others. There, the attraction was to take a simple dopant, because alkalis have one electron which is in the optical shell, and the rest of it forms a core. So it is a very nice, in some sense, a one electron system whose electronic structure is well known. So we studied that, but in that case, we also had some very nice surprises. So these are possible. People have studied, say, silver atoms, lead, and others. Even magnesium in helium atoms has been studied, has been doped into helium droplets and studied. There's a very nice experiment from the group of Josef Tickes Boimker and former division of Karl-Heinz Meyers-Breuer in Rostock, where they doped the helium droplet with magnesium atoms. And very interestingly, the magnesium atoms which form an aggregate inside the droplets don't sort of touch each other, of course, whatever touching means, but they form a foam-like structure in the neutral ground state configuration. But when they were excited with the laser, the foam collapsed, and the collapse of the foam would be caught in a laser spectroscopy experiment. So this is essentially quantum mechanics at its best, in the sense that the quantum interaction between the helium and the dopant atom, is the details of that determine the structure that is formed inside. There are some very nice papers from the group of Wolfgang Ernst, where they used helium droplets to grow silver nanowires and structures which otherwise are not easy to grow in room temperature conventional laboratory conditions. So they essentially grew hierarchical structures or networks of say silver atoms inside helium droplets, and they did a very clever thing. So once you take these droplets and form silver clusters, what you can in principle do is, this is a flying jet. You can essentially hold a surface, maybe even a cold surface at the end of the jet, like a stopper, that the jet goes and impinges on it, and it can deposit these structures, and then you can then take the structures after the heliums vaporize away and use it for something else, right? So this sort of a thing of depositing structures and using a grown helium droplets for growing them and depositing them as a technique has been explored by the group of Professor Ernst. And I'm sure there must be others, so apologies to those whose work I'm not citing right away.
Is
I
that
hope that answers your question, Sarah.
yeah, thank you.
Yes, it does. Thank you very much.
Thank you.
Okay, are there further questions, comments? So for those who are on YouTube, I wish you all the best. Have great holidays, have a great Christmas, New Year, wherever you're joining from and whatever these holidays are for you. And we are going to thank our speaker, Professor Krishnan, once more for his really nice talk, and take care, everyone.
Thank you, Carla. Merry Christmas and nice holidays and New Year to everybody online from me too.